This video is going to look at circuit theorems, which tells us that we can build an equivalent circuit that will take the place of an original and be much simpler. First of all, we're going to start out with the Thevenin equivalent circuit, and then we'll examine briefly Norton's theorem, which talks about the Norton equivalent circuit, and maximum power transfer theorem, and these are all related to Thevenin. So first of all, what is Thevenin? Thevenin says that there is an equivalent circuit that will behave the same as an original circuit from the perspective of the load, and this equivalent circuit will be presumably much simpler. Our equivalent circuit is always going to be an ideal voltage source in series with a single resistor. So that's as simple as it can get, and generally speaking, that would be simpler than any other circuit you're going to encounter. So we want to find how we get that equivalent circuit. What is the procedure for finding that equivalent circuit? And the procedure is this. First of all, open the load terminals, remove the load. Always have to work with the load terminals open. And then we have two steps, and you can do these in either order. First of all, we could determine the voltage across the open terminals. That becomes the Thevenin voltage. And the second step, or vice versa, you can do it in first if you want, is determine the Thevenin resistance. That would be the resistance looking in from the open terminals with the source removed. So let's look at an example. If we have this circuit here, a 10-volt source, and then 3 resistors connected to load terminals, what is the Thevenin equivalent of this circuit? So we're going to first of all open the load terminals. And now we want to analyze this in order to find what is the voltage across those open terminals. Well, in this case, look carefully, and that 100 ohm resistor connected to load terminals is connected to an open. Since it's connected to an open, there's no current flowing through the 100 ohm resistor. And if there's no current flowing through the resistor, there's no voltage drop across it. So the voltage will be the same on both sides of the 100 ohm resistor. So essentially what we're asking is what is the voltage across the 300 ohm resistor, since that would be the same as the voltage across the load terminals. Well, the voltage across the 300 ohm resistor turns out to be fairly straightforward. We can get that by simply using voltage divider, because again, the 100 is not influencing anything here. It doesn't play a role. So the Thevenin voltage, in other words, the voltage across the 300 ohm resistor, is simply the source voltage multiplied by the 300 divided by 300 plus 200. That's the voltage divider rule. If you do the arithmetic, you get 6 volts. That's the voltage across the 300, which is also the Thevenin voltage, which is what we're looking for. So we have the first step done. We found the Thevenin voltage. The next step is to find the Thevenin resistance. In order to find Thevenin resistance, remember we have to remove the sources. In this case, it was a voltage source, so replace it with a short. Had it been a current source, we'd replace it with an open. So our source is now removed, and we look in from the load terminals. What is that resistance? Well, we have the 100 ohm in series, and then we have a 200 and 300 in parallel. So write that out. We have 100 plus 200 parallel 300. And in order to get two resistors that are in parallel, how to find the equivalent resistance, we do product over sum. Product over sum, as you recall, only works if we have two different resistors in parallel. Will not work if you have more than two. So the Thevenin resistance then is 100 plus 200 times 300 divided by 200 plus 300. And do the arithmetic, you get 220 ohms. 220 ohms. So we're going to put that value of 220, associate that with our series resistor, and the voltage we found previously is 6 volts. This becomes our Thevenin equivalent circuit. And remember, with a Thevenin equivalent, if you're finding this, you should actually sketch out the circuit. Don't just put down the values of the resistor and the voltage source. Actually sketch the circuit and show that they are in series. Let's look at another example. Let's say we had this circuit. How would we find the Thevenin equivalent of this circuit? Well, we're going to follow the same procedure. The first thing we do is to remove the load resistor. And once we have the load resistor removed, we're going to determine the voltage across those open terminals. And in this case, it looks more complicated than it really is. Just like before, the resistor that's in series with the load terminal doesn't play a role. That would be the 40K. But also look down at the bottom of 50K. That's also connected to an open terminal. So likewise, that has no voltage drop. So the voltage across the load terminals is the same as the voltage across the 10K, because the no drop across the 40K and no drop across the 50K. So we're really just looking at the voltage across the 10K. And that voltage turns out to be fairly straightforward. We can use a voltage divider, 15 volts across the series combination of 20 and 10. So it's 15 times 10K, divided by 20K plus 10K. That would give us 5 volts. 5 volts then is our Thevenin voltage, because the voltage across 10K and the voltage across the load terminals are the same. So next thing we have to do is to look in from the load terminals and determine what is the Thevenin resistance. When we do that, we remove the source. So I've removed a 15-volt source, replaced with a short. Since that's shorted out, the 30K is also shorted out and really doesn't play a role here. So I've kind of grayed that out to remind you of that fact. Again, the 30K is shorted by the short replaced in there in place of the source. So in order to find that resistance, we see the 40K is in series, the 50K is in series, and in the 10 and the 20 are in parallel with one another. So our total resistance, 40K plus parallel 20K, 10K plus the 50K, and 40 and 50 is 90. Then we do the parallel. That works out to 96.7 kiloohms. 96.7 kiloohms. So our Thevenin equivalent looks like this: 5-volt source in series with a 96.7 kiloohm resistance. Let's look at this circuit. This circuit is a little bit more interesting. Here we're going to follow the same procedure in order to find the Thevenin equivalent. We first of all remove the load, and then we need to determine what is the voltage across that load terminal. Just like before, the 5K and the 6K don't play a role for the voltage. We need to find the voltage across the 1K. In order to do that, we're going to first of all find the voltage across the 2K and kind of work our way down. But the 2K has in parallel with the 4K and the 1K. So first of all, I'm going to combine that 4K and the 1K, and I'll represent that with a rectangular box. A rectangle is an alternate way of showing a resistance. You may not see that nearly as often, but I like to use it to represent a combination of resistors. So this rectangle actually represents the 10K, the 1K and the 4K combined into a 5K. 1K and 4K in series gives us 5K. Now that 5K is actually in parallel with the 2K, so we can find the combination, the parallel combination of the 2K and the 5K. And again, product over sum gives you 1.43 kiloohms. 1.43 kiloohms. That's in series of 3K. We can use the voltage divider, and that V2 would work out to 8.07 volts. I put that in blue because that is an intermediate answer. We're going to use that voltage across the 2K in order to find what we're looking for, which is the voltage across the 1K. So we'll go back to our original circuit. We just found the voltage across the 2K resistor. We can use that voltage along with voltage divider again using the 4K and the 1K. And we can get the voltage across the 1K, which turns out to be the Thevenin voltage. Do the arithmetic, that works out to 1.61 volts. 1.61 volts. So that becomes our Thevenin voltage. Now the Thevenin resistance, looking in from the load terminals, 5K and 6K are in series, but then we have a series parallel combination. Let's go work through them one step at a time. First, at 2 and 3, we're going to combine. 2 and 3 are in parallel. That works out to 1.2 kiloohms. That is in series with a 4K, so we get 5.2K in parallel with a 1. Okay, so 5.2 kiloohms in parallel with a 1K, and they're in series with a 5 and a 6. and you work that out, and you should get 11.8 kiloohms. 11.8 kiloohms. So now we have the 11.8 kiloohms. We have the voltage we did a minute ago, 1.61 volts. That is our Thevenin equivalent circuit. If we want the Norton equivalent circuit is a current source in parallel with a resistor. And the values turn out to be pretty trivial. The Norton resistance is the same as the Thevenin resistance. So once we find our Thevenin, we know our Norton. Those values are the same. The current, the Norton current, is simply Ohm's law. V Thevenin divided by R Thevenin. So in our first example, we had a 220 resistor in series with a 6-volt source. To convert that to Norton, we have the current source in parallel with the resistance. Current we're going to get by using Ohm's law. 6 divided by 220 gives us 27.3 milliamps. And the resistance is the same, 220 ohms. Maximum power transfer theorem. In this case, we're looking at the DC version. This is when we don't have any capacitors or inductors in the circuit. It simply says you get the most power transferred from the source to the load when the load resistance is equal to the Thevenin resistance of the source. So that occurs when RL is equal to R Thevenin. This is sometimes referred to as Jacobi's law. I don't hear that nearly as often. Most of the time you hear maximum power transfer theorem. But if you ever hear Jacobi's law, you know it's the same thing. Okay, so in our first example, the Thevenin resistance was 220. In order to get maximum power, we would simply make the load resistance 220 ohms. It's as simple as that. Don't make more of this than there is. All right, how do we use this? Let's look at an example of an audio amplifier. If the output of your amplifier says 4 ohms, then you should be connecting a 4 ohm speaker in order to get maximum power out. If you connect a 2 ohm speaker or a 6 ohm speaker, it's still going to work, but you're not going to get as much power out. So if you really want to rattle those windows when you're driving your car down, make sure your speakers match your amplifier. Same idea with an antenna. An antenna might have a Thevenin resistance of 50 ohms. You want to make sure your receiver has the same resistance value in order to match that and get as much power as you can from the antenna. Really important because the signal coming from the antenna is very, very weak, typically in the order of microvolts. So you want to get as much of that as possible, make sure it matches. You can try this circuit yourself. Okay, this circuit, pretty straightforward. I suggest you pause the video at this point and work this out, and then I will give you the answers, and hopefully they will agree. Okay, this actually turns out to be a fairly straightforward circuit. Once you remove the load, you want to determine the voltage there. The 100 doesn't play a role. So we have 200 in series with 200. So 12 times 200 divided by 200 plus 200, that is 6 volts. 12 times 200 divided by 400, or 1/2 of 12 is 6 volts. Looking in from the load terminals with the source removed, again the load is removed also, we have 100 in parallel with 200 parallel 200. And if you have two resistors in parallel and they're the same value, just divide by 2. So the 200 parallel 200 is 100. That's in parallel with, that's in series with the 100. So that gives you a total resistance of 200. So your equivalent circuit is 200 ohms, and the Thevenin voltage is 6 volts. Hopefully that's what you got when you tried to do this. So the Norton, again, the resistance values are the same, and the current, you just use Ohm's law, you get 30 milliamps. Okay, RL for maximum power, 200 ohms. All right. I hope you enjoyed the video. If you want to see more, look for Mark's Tech Talk on YouTube. Thank you very much.